Welcome to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now let's solve this problem from chapter 1, Fluid Mechanics by R.C. Hibbeler. The problem says that the tank contains 2 kg of air at an absolute pressure of 400 kilopascal and a temperature of 20 degrees C. If 0.6 kg of air is added to the tank and the temperature rises to 32 degrees C, determine the pressure in the tank. So initially the mass in the tank is, let's say, M1, which is 2 kgs, and the pressure P1 is 400 kilopascal. So 400 kilopascal is equal to 400 kilo is 10 raised to power 3 and pascal is Newton per meter square. And initial temperature T1 is 20 degrees C. So T1 in Kelvin will be equal to 20 degrees C plus 273. So 20 plus 273 is 293 Kelvin. So 293 Kelvin. Now the problem says that if 0.6 kg of air is added to the tank, so this means that mass 2 is equal to the initial mass plus 0.6. So initial mass is M1, which is 2, plus 0.6, this is 2.6 kgs. So the temperature rises to 32 degrees C. So T2 is 32 degrees C, which in Kelvin is equal to 32 plus 273. So 32 plus 273 is 305 Kelvin. So we are asked to find P2. Now using the gas law, we know that P2 will be equal to rho RT, or we can say rho 2 RT2. So rho 2 will be M2 divided by the volume of the tank R into T2. So we want to find P2. In this equation we have M2, we have R, we have T2, but we do not know the volume of the tank. So since we have the same tank for both the states, the volume is constant, we have to find the volume using the initial data. So from the initial data we can say that using the same equation, for the initial data we say that P1 is equal to rho 1 R T1, and again rho 1 will be M1 divided by the volume of the tank R into T1. So rearranging this equation we can say that volume of the tank is equal to M1 R T1 divided by P1. So just putting all the values, V volume of the tank is the mass M1, which is 2 kgs. R is 286.9 joule per kg Kelvin. So joule per kg Kelvin into T1. So T1 is 293 Kelvin divided by P1. P1 is 400 into 10 raised to power 3 Newton per meter square. Now as you guys can see, as we know that joule is work done and it is Newton meter, right? So 1 joule is equal to Newton meter. So we can say that joule is Newton meter. Since work done is F times D, so F is Newton and D is meter. So 1 joule is Newton meter. So now as you guys can see that we can cancel out this kg with kgs, and we can cancel out Kelvin with Kelvin. We can cancel out Newton with Newton. So in the numerator we are left with this meter, and in the denominator we are left with 1 divided by meter square. So ultimately this will give us meter cube. So the volume in the volume of the tank is 2 into 286.9 into 293 divided by 400 into 10 raised to power 3, and we have meter divided by 1 by meter square, which is ultimately equal to meter cube. So volume is equal to, we can say that volume is 2 into 286.9 multiplied by 293 divided by 400 into 10 raised to the power 3. So the volume of the tank is 0.420 meter cube. Now just putting this in this equation, we will be able to find P2 for the second state when the mass 0.6 kg mass is 18. So P2 is M2 is 2.6 kgs into R, which is 286.9 joule per kg Kelvin. So joule is Newton meter per kg Kelvin into T2, which is 305 Kelvin, and divided by the volume. Volume is now 0.42 meter cube. Now again cancelling out the units, so kg will cancel out with kg, Kelvin will cancel out with Kelvin, and 1 meter will cancel out with this meter cube. We will be left with meter square. So P2 is equal to 2.6 into 286.9 into 305 divided by 0.42, and in the numerator we have Newton, and in the denominator we have meter square, which is Pascal, right? So Newton per meter square is Pascal. So this is, we can have P2 equal to 2.6 multiplied by 286.9 multiplied by 305 divided by 0.42. So this gives us P2 equals to 541,694 approximately Newton per meter square. And if you want to write it in kilopascals, since this is a large pressure, so we have to multiply and divide it by thousands. Newton per meter square. So if I divide my answer by 1000, so which is 541.694, so we can say that 541.694 and 1000, this 1000 is kilo, right? So we can say that this is kilo, and Newton per meter square is Pascal. So P2 is, we can say that P2 is approximately equal to 542 kilopascal. So this was the required pressure when the mass was added. When 0.6 kg mass was added, the temperature raised to 32 degrees C. So as a result, the pressure is 542 kilopascal. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from fluid mechanics by R.C. Hibbeler.